Hello there, and welcome to the Sleepy Science Channel. Tonight, we are going to travel somewhere very wide and very deep. We are going to spend our time together near water, near the great, gentle, ancient ocean, and near the quiet rivers that wind their way through forests and meadows and valleys to reach it. And along the way, we are going to ask a very peaceful question, not a difficult one, not one that requires you to think too hard. Just a soft, curious question that has a beautifully simple answer. Why is the ocean salty, but rivers are not? You have probably tasted it before, that first unexpected mouthful of seawater on a summer day. That sharp, full mineral taste that seems to belong to the sea the way blue belongs to the sky. And yet, you have also cupped your hands in a cold mountain stream and drunk from it like an animal, clean and sweet and light as air. What makes them so different? What happened along the way? The answer is slow and old and beautiful. It involves rain. It involves stone. It involves millions of years of rivers carrying tiny, invisible gifts from the land to the sea, and the sea quietly keeping every one of them. It is one of those stories that begins before any creature existed to watch it happen, and it is still happening right now as you lie here, breathing softly, beginning to let go of the day. So let's begin. Let's begin at the very beginning, where all water begins, high up in the sky. All the water in the world is the same water, moving in a slow, endless circle. It always has been. The water that falls tonight as rain over a sleeping forest may have been ocean water just a few months ago, lifted into the clouds by the warmth of the sun. Imagine standing at the edge of the ocean on a warm afternoon. The surface of the water shimmers, and invisibly, constantly, tiny molecules of water are rising from that surface into the air above. Not as mist. You can't see them. They just drift upward, weightless and invisible, becoming part of the atmosphere. This is called evaporation, and it is one of the most important and quiet processes in the whole world. The sun's warmth reaches down and gently lifts water molecules from oceans, lakes, rivers, puddles, and even from the surfaces of leaves. But here is the beautiful part. When water evaporates, it leaves everything else behind. The salt stays in the sea. The minerals stay where they are. Only the water itself rises. It rises clean and pure as anything in nature, and drifts on the wind toward the clouds. When enough water vapor gathers high in the cold air, it condenses into tiny droplets. Those droplets come together around tiny particles of dust and form clouds. And when the droplets grow heavy enough, they fall back down as rain. Rainwater, when it first falls from a cloud, is almost perfectly pure. It has almost nothing dissolved in it. It is as clean and empty as water can be, a soft blank page. That blank page is what falls onto the mountains. That blank page is what soaks into the soil. That blank page is what begins to flow downhill, very slowly at first, in tiny threads, gathering into streams, gathering into rivers, and as it flows, it begins very slowly and gently to pick things up. This is where the story of salt begins, not in the sea, but in the stone. Right now, somewhere high in a mountain range, rain is falling quietly on bare rock. And that rain, clean and soft as it is, begins to do something ancient. It begins to dissolve the rock just a little, just a few invisible atoms at a time. So slowly, you would never notice if you watched for an hour or even a year. But the water and the stone have been doing this together for billions of years, and they are very patient. Let that image stay with you for a moment. Rain on stone, patient, soft, unhurried. The mountain slowly giving its minerals to the water carrying them gently downhill. Nowhere to rush, nowhere to be. Rocks are not as solid as they appear. If you could look at them closely enough, more closely than any eye can see, you would find that they are made up of crystals and minerals, packed together tightly, each one a slightly different shape, a slightly different color, a slightly different chemistry. There is calcium, which is the same mineral that makes your bones strong. There is magnesium, soft and silvery. There is potassium, which helps plants grow. There is silica, which makes glass. There is iron, which makes old rocks look rust-colored in the afternoon sun. And there is something called sodium. Sodium is a soft, almost ghostly metal that, in its natural form, dissolves very easily in water. When sodium meets certain other elements, especially chlorine, it forms a compound called sodium chloride. You know it by a simpler name: salt. Sodium is everywhere in the crust of the earth. It sits quietly in granite and limestone and sandstone and basalt, waiting. And when rain touches those rocks, especially slightly acidic rain, which most rain is, having passed through the carbon dioxide in the air, the sodium begins very slowly to be released. Carbon dioxide from the air dissolves into rainwater and forms a very mild acid called carbonic acid. It is far too weak to hurt anything. It is gentler than lemon juice, gentler than vinegar. But it is just acidic enough to coax minerals out of rock over thousands and thousands of years. So every river in the world carries a little bit of dissolved mineral within it. Not much, usually far too little to taste. A river tastes clean and light because the amounts are so small. But they are there, flowing, invisible, patient. The Amazon River carries minerals from the ancient rocks of South America. The Nile carries minerals from the mountains of Central Africa. The Rhine carries minerals from the Alps. Every river is carrying its quiet cargo of dissolved stone toward the sea. And the rivers have been doing this for a very long time, for hundreds of millions of years. Since before the first fish swam, since before the first flower bloomed, since before the first footstep was ever made on land. The rivers have been flowing, and the rivers have been carrying. Take a slow breath and let yourself imagine all those rivers all over the world, all flowing quietly toward the sea, each one carrying its invisible gift of minerals, each one part of the same ancient story. Let's follow a single raindrop on its journey. It falls on a hillside somewhere. Let's say a green, mossy hillside in a place where forests grow thick and the air smells of pine and wet earth. The raindrop soaks into the soil. The soil is full of tiny spaces like a sponge, and the water passes through them slowly, filtering through layers of clay and sand and root and stone. It picks up a little calcium from a piece of limestone it passes near. It picks up a little potassium from the soil, a trace of magnesium. Almost nothing, just atoms, just whispers. Eventually it reaches a layer of rock it cannot pass through, and it turns sideways, flowing underground through the dark until it finds a crack or a spring, and it emerges, blinking, you might say, into daylight, as part of a small, cold, clear stream. That stream joins another stream. The two of them flow together, gathering speed around mossy rocks, over gravel beds where small, flat stones rattle in the current. A leaf falls in and floats for a while. A bird lands on a rock in the middle and looks around and flies away again. The stream grows into a river. The river grows wider. The banks grow farther apart. The water slows from quick and chattering to something more like breathing, deep and rhythmic and unhurried. Trees lean over the banks and dip their leaves in. All the while, the water is carrying its invisible cargo, not just the minerals it picked up from the hillside. It has been collecting more along the way. A little more calcium, where limestone cliffs rise near the banks. A little silica from beds of sandy rock. Tiny traces of iron from reddish clay. These amounts are so small that if you dipped a glass in the river and held it up to the light, the water would look perfectly clear. You could drink it and taste nothing unusual. And yet, if you could evaporate that glass of river water and look at what was left behind on the glass, you would see a faint ring of white mineral residue. The rivers do carry salt, just not enough to taste. And eventually, after days or weeks or months of traveling through meadows, through canyons, through cities, through marshes, the river reaches the coast. The land runs out. The river spreads into an estuary, wide and shallow and tidal, where fresh water and salt water meet and mingle in slow, shifting patterns. And then, gently, without ceremony, without any particular announcement, the river becomes the sea. The place where a river meets the ocean is one of the most peaceful places on earth. Estuaries, they are called. And they are soft places, in between places, where the rules are a little looser, where fresh water and salt water drift together in slowly mixing layers. Salt marshes grow at these edges, low, green, windswept. Grasses that can survive in salt water sway gently in the tidal breeze. Herons stand motionless in the shallows, watching. Tiny crabs move sideways through the mud. Everything here moves with the rhythm of the tides. The minerals that the river has been carrying, all that calcium and sodium and magnesium and potassium, flow into the estuary and then into the open sea. And here, something very important happens. Something that has been happening for hundreds of millions of years. The sea keeps them. When water evaporates from the ocean, as it does all day, all night, ceaselessly, from every square inch of ocean surface around the world, it takes only the water molecules, it leaves the minerals behind. The salt cannot evaporate. It is too heavy, too different, too bound to the water it lives in. So it stays. The rivers bring more minerals. The water evaporates and takes nothing with it. More minerals arrive. More water leaves. Over millions and millions of years, the minerals accumulate. They concentrate slowly. The way tea becomes stronger, the longer it steeps. The ocean is the cup, time is the heat, and the minerals are the flavor. This is why the ocean is salty. Not because it was always salty from the beginning, though we sometimes imagine it that way. It became salty gradually, over an almost incomprehensible length of time, through the patient work of rain and rivers and stone. Scientists estimate that the oceans have been accumulating salt for somewhere around 3 to 4 billion years. Think about that softly, without trying to truly grasp it. Let it just rest in your mind like a stone resting at the bottom of a stream. 3 to 4 billion years of rivers bringing salt to the sea, and the sea quietly keeping every grain. If you're enjoying this story, please feel free to leave a comment below. We'd love to know what you're thinking about as you drift off. And a like really helps the channel grow, so more tired souls can find their way here. The ocean is about 3.5% salt by weight. That means that in every 100 grams of seawater, about 3.5 grams of that weight is dissolved salts. It doesn't sound like very much, but it adds up to an almost unimaginable quantity of salt spread through the world's oceans. If you could take all the salt out of the ocean and spread it over all the land on Earth, it would form a layer about 40 stories high. Every mountain, every plain, every desert and forest and city on every continent covered under 40 floors of salt. That is how much the sea has collected over its long, patient life. The most common salt in the ocean is the same salt you find in your kitchen: sodium chloride, ordinary table salt. It makes up about 85% of the dissolved minerals in seawater. The remaining 15% is a mixture of other minerals: magnesium, sulfate, calcium, potassium, bicarbonate, and many, many others in very small quantities. The saltiness of the ocean is remarkably consistent around the world. Whether you are in the warm blue waters of the Caribbean or the cold gray seas near the Arctic, the salt content is surprisingly similar. Ocean currents mix the water constantly, distributing the minerals evenly like a slow, global stirring. Some seas are saltier than others. The Dead Sea, which is actually a lake with no outlet, is 9 times saltier than the ocean. Nothing can live in it except certain hardy microbes. You can float in it effortlessly. Your body is less dense than the water, and so you simply rise to the surface and rest there as if you were lying on an invisible mattress. The Mediterranean Sea is a little saltier than average because it is almost enclosed by land, and evaporation is strong there. The Baltic Sea in the north of Europe is much less salty because so many rivers flow into it and rainfall is heavy, diluting the salt. Each sea has its own character. Each one holds its minerals in its own particular balance. But they are all connected in the end, all part of the same great ocean that wraps around the earth, that has been there since before anything breathed, that holds more life within it than we have yet imagined. Take a breath. Let your body feel heavy and soft against whatever you are resting on. Imagine the surface of the ocean at night, dark and quiet and very slightly luminescent, moving in long, slow swells. The salt is there, dissolved and invisible, carried by all the rivers of all the centuries. There is another source of salt in the ocean, one that has nothing to do with rivers, one that comes from deep within the earth itself. Beneath the ocean floor, in places where the tectonic plates of the earth's crust pull apart, there are cracks in the rock, deep, narrow fissures where the ocean water seeps down into the hot stone below. Down there, far below the surface, the water is heated to extraordinary temperatures by the magma beneath the crust, and as it heats, it reacts with the surrounding rock, dissolving minerals, especially metals and sulfur compounds, from the deep rock in ways that surface water never could. Then, full of dissolved minerals, the water rises back up through the cracks and emerges on the ocean floor as a hydrothermal vent. The water that emerges can be extraordinarily hot, sometimes over 300 degrees Celsius. But because of the immense pressure at those depths, it doesn't boil. It billows out in dark clouds of dissolved minerals, like smoke from a chimney, so thick with sulfur and metals that it stains the water dark gray or black. These plumes are called black smokers, and they have been adding minerals to the ocean from below, just as rivers add minerals from above, for as long as the ocean has existed. Around hydrothermal vents, in the complete darkness of the deep ocean floor, far from any sunlight, extraordinary communities of creatures live. Tube worms as long as your arm, swaying in the warm current. Ghostly white crabs feeling their way across the rocks. Tiny shrimp clustered near the vents like moths near a flame. These creatures survive not on sunlight, but on chemical energy, a process called chemosynthesis, where bacteria break down sulfur compounds and use that energy to build food. It was the discovery of these communities in the 1970s that changed the way scientists thought about where life might exist in the universe. If life can flourish in complete darkness, under crushing pressure, fed by chemicals from volcanic rock, then perhaps life is not as rare as we once thought. But tonight, you don't need to think too hard about any of that. Just hold the image gently in your mind. The deep ocean floor, dark and warm, near the vents, teeming quietly with life that has never seen the sun. The minerals rising from the earth's heart into the water above. The whole ocean breathing in its slow geological way. The ocean is not still. Even in its deepest places, it is always moving, always exchanging, always turning over the minerals that make it what it is. Here is a gentle puzzle that you might have already begun to wonder about. If rivers carry minerals from the land to the sea, why don't the rivers themselves become saltier over time? If they are always picking up a little mineral here and there, why does river water stay so clean and fresh? The answer is beautiful in its simplicity. It comes back to the water cycle. When rain falls, it falls as pure water. The salt and minerals stayed behind when the ocean water evaporated. So every raindrop that falls on a hillside is carrying a fresh supply of clean, mineral-free water. The water that soaks into the rock and picks up minerals as it flows downhill is constantly being replenished by new, clean rainwater falling from above. Think of it like a gentle conveyor. Clean water falls. It picks up just a few minerals as it moves through rock and soil. It carries those minerals to the sea. The sea keeps the minerals. The water evaporates from the sea, clean again, rises to the clouds, falls as rain, clean again. Always clean. The river is always being topped up with fresh water, so it never has the chance to accumulate salt. The concentration stays very low, almost constant, because the flow is continuous and the rain is always renewing the supply. The ocean, on the other hand, has no such outlet. It has no drain, no overflow pipe, nowhere for the minerals to go once they arrive. The water can leave through evaporation, but the salt cannot. And so the salt stays and more salt comes, and the concentration builds very slowly over time. The ocean is essentially a vast mineral collector, billions of years of rivers flowing into it, each one carrying its tiny invisible load, and no way for those minerals to escape. It is one of the most elegant and patient systems in all of nature. Some minerals do leave the ocean, of course. Some are incorporated into the shells of sea creatures. Calcium becomes the hard, white, intricate architecture of coral and oysters and sea snails. Some minerals settle to the ocean floor as sediment and eventually become rock again, completing a cycle that spans hundreds of millions of years. The salt in the ocean is not infinite. It has reached something close to an equilibrium. The amount arriving from rivers roughly balances the amount being removed into sediment and sea creatures. The ocean has been approximately this salty for hundreds of millions of years. It is stable. It is settled. It has found its balance. If you'd like more stories like this one, slow, peaceful, curious, do check out the playlist on the channel. There are nights of stars and forests and rain, nights of mountains and rivers and wind. They'll be there whenever you need them. Salt and water together do something remarkable. They create the conditions for life. Almost all life on Earth, whether it lives in the sea or on land, whether it swims or walks or crawls or grows in the ground, carries a little piece of the ocean inside it. The fluids in your blood, your cells, your tears are salty. Not as salty as the sea, but salty in the same way, with the same minerals. This is not a coincidence. Life began in the ocean billions of years ago, in those ancient warm seas. The very first living cells formed in water that was salty, and they built themselves to work in that environment. When life eventually came ashore and left the ocean behind, it carried the memory of the sea within it, sealed inside its own fluids. Your body maintains a salt concentration in your blood that is very close to the salt concentration of the ancient ocean, not the modern ocean, which has grown saltier over time, but the ocean as it was several 100 million years ago, when our distant ancestors first developed blood. We are all, in some sense, carrying ancient seawater inside us. Sodium is essential to how your nerves work. Every thought you have, every sensation you feel, travels through your nervous system as an electrical signal. And that signal depends on sodium ions moving in and out of cells. Without sodium, without salt, your nervous system would be silent. There would be no signal to carry the sense of softness of a blanket, the warmth of a bed, the sound of quiet breathing. Potassium, which rivers also carry to the sea, works alongside sodium to keep your heart beating. Calcium, carried by rivers from limestone hills, strengthens your bones and helps your muscles contract. Magnesium, dissolved from ancient rock and carried by 1,000 rivers to the sea, helps your body make energy and keeps your muscles relaxed. All of these minerals, which were locked in rock, released by rain, carried by rivers, and accumulated over billions of years in the sea. These same minerals now flow quietly through your body as you lie here, soft and still, beginning to rest. The story of salt is also the story of you. You are made of old, patient chemistry, river-carried, ocean-kept, slowly gathered across geological time. You are, in a very real sense, a small piece of the world's most ancient story. Have you ever stood at the edge of the ocean and just breathed? Even before you see the water, even from a distance, you can smell it. That particular sharp, clean, mineral smell that belongs only to the sea. It is one of the most recognizable smells in the world. Sailors knew they were near land or water by smell before they could see it. That smell is partly salt, sodium in the air, tiny particles lifted from sea spray. But it is also something called dimethyl sulfide, a gas produced by tiny marine algae and bacteria that live in the surface layer of the ocean. They produce it as part of their chemistry, and it drifts into the air in enormous quantities, giving the coast its particular perfume. The sound of the sea is also partly about salt. Salt water is denser than fresh water because of all the dissolved minerals. Sound travels faster through it, about 1,500 meters per second in salt water compared to about 1,480 meters per second in fresh water. The difference is small, but in the vast depths of the ocean, it adds up. Whale songs can travel thousands of miles through the sea. The color of the sea is influenced by salt too, in subtle ways. The blue of clear ocean water comes mostly from the way water molecules absorb red wavelengths of light and scatter blue ones. But the minerals dissolved in the water affect how the light passes through it, contributing to the shifting greens and blues and purples that the ocean shows in different lights and at different depths. At sunset, standing on a beach, the ocean can look like it is made of metal, copper near the horizon, bronze where the waves catch the low light, dark gray in the troughs. And through all of that color and light and motion, the salt is there invisible, tasting of ancient geology. There are animals that have evolved specifically to live at the boundary between salt and fresh water, creatures that can adjust their body chemistry as they move between rivers and sea. Salmon are the most famous of these. They are born in cold, fresh rivers, spend years in the open ocean, and then return, guided by the memory of the exact chemical signature of the river they were born in, to lay their eggs in the same cold stream where they themselves began. The transition is extraordinary. As a salmon moves from fresh water to salt water, its entire body chemistry shifts. Cells that were working to keep salt in begin to work to keep salt out. Hormones change. The kidneys change how they filter the blood. The fish transforms itself biochemically from a freshwater animal to a saltwater animal, and then, years later, transforms itself back. It is one of the most remarkable things a living body can do, and it is all about salt, about the difference between the river and the sea. The ocean is not the only place that accumulates salt. There are lakes around the world, some small, some enormous, that sit in enclosed basins with no outlet. Rivers flow in, bringing their minerals, but no river flows out. And over thousands of years, these lakes become salty. The Great Salt Lake in Utah, in the American West, is one of these. It is the remnant of an ancient, much larger lake called Lake Bonneville, which existed during the last ice age and covered much of the region. As the climate warmed and dried, the lake shrank, and the minerals that had washed into it concentrated. Today, the Great Salt Lake is several times saltier than the ocean. The shore of the Great Salt Lake is encrusted with salt crystals, white and glittering in the sun, crunching softly underfoot. Billions of brine shrimp live in the water, small as your smallest fingernail, tinted pink, moving in vast pink clouds through the briny water. They are one of the few creatures on Earth that can thrive in water that salty. Flamingos gather at similarly salty lakes in Africa, the soda lakes of the Rift Valley, like Lake Nakuru and Lake Bogoria. These lakes are rich not just in sodium chloride, but in sodium carbonate, which makes the water alkaline as well as salty. The flamingos wade into the shallows in their millions, filtering tiny algae called spirulina from the water. The spirulina gives them their famous pink color. Imagine those lakes at dawn, the still alkaline water reflecting the pale sky, the flamingos standing in their vast pink crowds, the air full of the sound of their low, gentle calls, and around the edges of the water a pale crust of salt, white as snow. There is something quietly astonishing about the way life adapts to salt. Salt that seems extreme to us, too strong, too mineral, too much, becomes simply home to creatures that have evolved to live within it. The brine shrimp, the flamingo, the salt-tolerant shrubs that grow at the edges of salt flats. All of them have found a way to make peace with the mineral that rivers carry to the world's enclosed spaces, even in the driest places on Earth, in salt flats that look completely lifeless. Great flat expanses of white, dazzling in the midday sun, where no plant grows and no bird lands. Even there, a few microbes persist. Halophiles, they are called, salt lovers, living slowly in the brine, happy in a world that most creatures would find impossible. Life finds its way everywhere. It always has. Do leave a comment if this kind of story helps you unwind. It means so much to know you're out there, resting quietly. And if you haven't already, the playlist is full of more nights like this one. Let's return for a moment to where this story began, to the rain on the rock, because there is something gentle and wonderful happening in that moment that is worth paying attention to. When rain falls on rock, it does not just wash over it. It seeps into tiny cracks. It works its way between mineral grains, and because it is very slightly acidic, remember the carbonic acid, softer than lemon juice, gentler than anything you would notice, it begins to react with the minerals in the rock. This process is called chemical weathering, and it is one of the great slow forces that shape the surface of the earth. Not as dramatic as earthquakes, not as visible as erosion by rivers, but persistent, intimate, and ancient. Different rocks weather at different rates. Limestone, which is made mostly of calcium carbonate, dissolves relatively quickly in acidic rain. That is why limestone landscapes are full of caves and sinkholes and underground rivers. The water has slowly dissolved its way through the rock, creating hollow spaces, carving passages that might take thousands of years to form. Granite, on the other hand, is much harder and weathers slowly. It stands in mountains for hundreds of millions of years. But it weathers too, slowly, patiently, grain by grain. The minerals in it are released, one atom at a time, into the water that seeps through its cracks. Feldspar, one of the most common minerals in granite, weathers into clay. As it weathers, it releases potassium and sodium into the water. Those ions make their way into streams, into rivers, and eventually to the sea. The clay stays behind on the hillside, giving the soil its fine texture, its ability to hold moisture, its rich, dark color. Quartz, another common mineral in granite, is much more resistant. It doesn't dissolve easily. Instead, it breaks into smaller and smaller grains, sand. The sand washes into rivers and eventually reaches the coast, where it accumulates on beaches. Most of the sand on most beaches is quartz. It is the last remnant of mountains, ground down by water and time, until all that is left are these round, pale, smooth grains, warm in the sun, cool at the water's edge. Somewhere on a beach tonight, grains of sand that were once part of a mountain are resting in the dark. Waves are moving over them gently. They have been on this journey for millions of years. They are patient beyond any patience you could measure. The ocean remembers everything, not with memory as we understand it, not with thoughts or feelings or dreams, but with layers, with chemistry, with the slow accumulation of time recorded in sediment and stone. On the ocean floor, far below the waves, far below the reach of any current, sediment settles like soft snow, constantly, slowly, year after year after year. Tiny shells of microscopic creatures, dust blown from deserts, volcanic ash from eruptions, silt carried by rivers and dropped when the water stills. Layer upon layer, millimeter by millimeter, building up over millions of years. Scientists drill through these layers and bring up long cylinders of sediment, cores that span hundreds of thousands of years of history. Reading them is like reading a book written by the ocean itself. Changes in the mineral composition of the sediment tell you about what the climate was like. The presence of certain microscopic fossils tells you about water temperature. The chemistry of tiny foraminifera shells, each one smaller than a grain of sand, tells you about the salt and mineral content of ancient oceans. Through these sediment cores, scientists have traced the history of the ocean's chemistry going back hundreds of millions of years. They have found that the ocean has been approximately as salty as it is now for at least the past 600 million years, since before the first fish existed. The equilibrium between salt arriving and salt being incorporated into seafloor sediment has kept the ocean in a stable, life-sustaining range. This is one of the most remarkable things about the Earth. Its systems self-regulate. The carbon cycle, the water cycle, the salt cycle, they all have feedback loops, checks and balances, ways of keeping themselves stable over long time periods. Not perfectly stable, not unchanging, but resilient. The ocean has been hospitable to life for billions of years because its chemistry stays within a range that life can work with. When you look at the ocean, you are looking at something that has been finding its balance for longer than your imagination can comfortably hold. It has been patient with ice ages and warm periods and mass extinctions and the slow drift of continents. It has absorbed the minerals of 1,000 mountain ranges that have risen and eroded away to nothing. And it is here now, wide and dark and calm, its salt content steady, its deep memory intact. There is something very reassuring about that, about the steadiness of the sea, about the way it has been there through everything, holding its minerals, breathing with its tides, keeping its temperature and chemistry within the range that allows creatures like you to exist. You are, in this moment, resting on a planet covered in an ancient, self-regulating ocean. The planet knows what it is doing. It has been doing it for a very long time. Let's return to the rivers for a while, to the sound of them and the feel of them and the way they look in different lights. A river in a forest sounds different from a river on a plain. In a forest, the water moves quickly over stones and roots, making that quick, bright, chattering sound. The sound of light on water, of restlessness. The banks are close together. The light comes in between the branches in moving patches, dappling the water. On a plain, the river is wide and slow and almost silent. It moves so gently that you can sometimes only tell it is moving by watching a floating leaf drift past. The surface is smooth enough to reflect the clouds. It makes a soft, susurrant sound when the wind touches it, like breathing, like the sound of someone turning over in their sleep. In a mountain river, the water is cold. cold in a way that makes your hands ache after a few seconds. Cold the way mountain snow melt is cold. The water is clear, so clear you can see every pebble on the bottom, every shadow of a trout hanging in the current. The sound is loud and rushing and white, and you have to raise your voice to be heard over it. All these rivers in their different moods are carrying their minerals to the sea. The forest river picks up a little tannin from the roots and leaves, which turns it tea-colored in some places, dark amber in the shallows, almost black in the deep pools. The plain river carries fine silts. The mountain river carries small gravel and sand. The Amazon River, the largest river in the world by volume of water, is divided into two kinds: the black water rivers and the white water rivers. The black water rivers flow through ancient, nutrient-poor soils and are stained dark by dissolved organic matter, like very weak tea. The white water rivers carry suspended sediment from the Andes and are the color of milky coffee. Where they meet, the two colors flow alongside each other for miles before finally mixing, like two separate thoughts slowly becoming one. Even in a city, the river is still doing its ancient work, covered in concrete banks, crossed by bridges, carrying the reflections of lights, but still flowing, still picking up minerals, still making its way to the sea. The river is patient with cities the way it is patient with everything. Cities come and go. The river endures. And at the end of every river's journey, the same quiet moment, the water spreading out into the estuary, the salt beginning to rise in the water column as the fresh water floats on top of the heavier salt water beneath, and then the final gentle dissolution into the sea. The minerals delivered, the river's work for that particular drop of water complete. If you found your way here for the first time tonight, welcome. There's a whole playlist of stories waiting for you. Trees and stars and rain and deep ocean nights. It's all there whenever you need it. There is one more force that shapes the salt of the sea, and it comes from the sky, not as rain, but as snow, as ice. During the great ice ages, when sheets of ice several miles thick spread across enormous portions of the continents, vast quantities of water were locked up on land. Glaciers grew, sea levels dropped by as much as 120 meters at times, enough to expose land bridges between continents, enough to reveal the shallow sea floor as dry land. When that much water is locked up on land, the ocean shrinks in volume. And when the ocean shrinks but the salt stays constant, the salt concentration rises. The ocean of the last ice age, 20,000 years ago, was somewhat saltier than the ocean today. Not dramatically, but measurably. The sea was denser, colder, and slightly more mineral-rich. And when the ice melted, slowly, over thousands of years, enormous rivers of meltwater poured into the sea. These rivers of meltwater were pure, clean, mineral-free water because they had been locked in ice, unable to react with rock. They diluted the ocean slightly, easing its saltiness back toward the balance it holds today. Glaciers, while they exist, do something remarkable to the rock beneath them. They grind. Slowly, with enormous weight, a glacier moves across rock and grinds it down. The rock flour produced by this grinding, a fine powder of mineral, is carried by meltwater streams at the glacier's edge, giving those streams their distinctive milky turquoise color. Glacial melt rivers are often this pale blue-green, beautiful and otherworldly, heavy with ground stone. Some of the most striking rivers in the world are glacial rivers. In Iceland, in Patagonia, in the mountains of New Zealand, meltwater rivers run that particular impossible turquoise, the color of ground mineral, of rock reduced to dust, suspended in cold water in the full light of a high-latitude afternoon. Those rivers, too, are carrying their mineral load to the sea. The glaciers are grinding stone that has not been touched by water for thousands of years, releasing fresh mineral stores into the global ocean cycle. In this way, even the ice is part of the story of salt, grinding, releasing, delivering, renewing. Right now, in this moment, somewhere in the world, a glacier is moving so slowly you would not be able to perceive it even if you sat and watched for an hour. But it is moving, it is grinding, it is releasing, and the meltwater is finding its way to a stream, and the stream to a river, and the river to the sea. Everything moves, even the ice, even a stone. They just move on a different kind of time than we do, a longer, more patient kind of time. And that is strangely comforting if you let it be. The world moves slowly and surely and has always found its way. The ocean is not a passive container of salt. It is alive, profoundly alive, with creatures that are constantly interacting with its chemistry, consuming minerals, releasing them, building structures from them, dissolving those structures again after death. Oysters, clams, mussels, scallops, bivalves, these creatures are called, meaning two-valved, two-shelled. They spend their lives fixed in one place, drawing seawater through their bodies, filtering out tiny particles of food, and using the calcium dissolved in the water to build their shells. A single oyster can filter several liters of water every hour. A bed of oysters in an estuary filters the water of an entire bay. The shell of an oyster is made of calcium carbonate, the same mineral that makes up limestone, the same mineral that dissolves in slightly acid rain and flows in rivers to the sea. The oyster has taken the sea's dissolved mineral and turned it into architecture, into a home, into the smooth, curved, pearlescent structure that you find washed up on a beach after a storm, pale and beautiful. Coral reefs are perhaps the most dramatic example of living creatures building with the sea's minerals. A coral reef is not a rock. It is a construction project that has been ongoing for millions of years, built entirely by tiny animals called polyps, each one no bigger than your thumbnail, each one secreting a tiny cup of calcium carbonate around its soft body. A single coral polyp is almost nothing, but billions of them, over thousands of years, can build a structure visible from space. The Great Barrier Reef off the coast of Australia is over 2,000 kilometers long. It is the largest living structure on Earth, and it is made of the same calcium that rain dissolved from limestone hills and rivers carried to the sea. When coral polyps die, their calcium carbonate skeletons remain. New polyps grow on top of them. Over time, layer upon layer, the reef builds upward. The living part of a coral reef is only the outer surface. The interior is the compressed history of all the polyps that came before, their tiny cups of calcium stacked and cemented into stone. Some of the calcium in an ancient limestone cliff, the white cliffs you see along coastlines in temperate countries, is made entirely of the compressed shells and skeletons of ancient sea creatures. What looks like solid rock is actually a library of tiny lives, each one a creature that filtered calcium from a Cretaceous sea, built a shell around itself, lived and died, and sank slowly to the seafloor to become, over millions of years, stone. And that stone, raised by tectonic forces into cliffs, will be dissolved by rain, carried by rivers, returned to the sea. The calcium will be filtered again by oysters and coral and foraminifera. Life endlessly recycling what the earth provides, in circles so large and slow they barely register as circles at all. Let your breathing slow. Think of the oyster on its rock, drawing water through its body. Think of the coral polyp in its warm, sunlit sea, quietly building. Think of all the circles, all the returns, all the patience written into the chemistry of the world. You're doing so well, resting through this story. If you'd like to leave a like or a comment, we'd love to hear from you. And do explore the playlist if you need more nights like this one. There's always more waiting for you there. The tide is the ocean's breath. Twice a day in most places the sea rises, slowly, inexorably, covering the rocks and pools and sand that were exposed just hours before. And twice a day it falls again, pulling back to reveal all that it had covered, leaving behind pools of water, stranded creatures, glistening seaweed. The tide is caused by the moon. The moon's gravity reaches across space and gently pulls at the ocean, raising a slight bulge of water on the side of the earth facing the moon, and a corresponding bulge on the far side. As the earth rotates, these bulges move around it, and the places they pass over experience high tide. The moon has been pulling at the ocean for over 4 billion years. In the early days of the earth, the moon was much closer, perhaps 3 times closer than it is now. And the tides it raised were enormous, possibly hundreds of meters high, sweeping across vast shallow seas on a young, largely landless planet. Over billions of years, the tidal friction has gradually slowed the Earth's rotation. Days were shorter in the distant past, perhaps only 6 hours long when the Earth was very young. The energy that goes into the tidal bulge is slowly, gently breaking the planet's spin. And as the Earth's rotation slows, the moon drifts a little farther away. It is still drifting now, moving about 4 centimeters farther from Earth each year. The tides mix the ocean. They push water back and forth across the shallow coastal margins, the estuaries, the continental shelves. They stir sediment. They bring nutrient-rich water from the deep up to the sunlit surface. They carry the ocean's salt into crevices and rock pools and salt marshes where it has shaped the entire ecology of those places. A rock pool is a small world left behind by the tide, filled with seawater, salty, mineral-rich, and exposed to the sun for hours at a time. As the sun heats the pool and water evaporates from its surface, the pool becomes saltier than the open sea. Creatures that live there have adapted to a wide range of salt concentrations. Sea anemones, small crabs, periwinkles, sea stars. All of them have bodies that can handle the shifting chemistry of a world that is alternately drowned and exposed. At low tide, a rocky coastline is one of the most quietly alive places on Earth. Every crevice holds something. Every pool contains a whole drama of small creatures going about the slow business of feeding and sheltering and waiting for the tide to return. And all of it, all that life, is dependent on the salt that rivers carried to the sea, that the ocean accumulated over billions of years, that the tide now brings to the shore. Somewhere right now, the tide is going out. The water is pulling back from a dark beach, leaving wet sand that catches the moonlight. The salt smell is strong. The sound of the waves is softening as the water retreats, and the rock pools are settling into their quiet nighttime lives. The sea stars motionless on the stones, the anemones gently closed. Not all rivers run on the surface where you can see them. Some flow underground through caves and passages carved in limestone over thousands of years by the patient acid of rainwater. These are called karst landscapes, named after a region in Slovenia where such underground rivers were first studied carefully. In a karst landscape, the ground above can look ordinary, fields, trees, gentle hills. But beneath your feet, if you walked across it, the ground would be hollow in places, threaded through with passages, chambers, underground rivers, lakes, a perfect still water that have never seen sunlight. The water that carved those passages is the same water that carries salt to the sea. It fell as rain. It became slightly acidic with dissolved carbon dioxide. It found cracks in the limestone and began very slowly to dissolve them wider. A millimeter wider in 100 years, a centimeter in 1,000. Over tens of thousands of years, small cracks became passages, passages became tunnels, tunnels became chambers large enough to swallow a cathedral. Inside these caves, something beautiful happens with the minerals the water carries. As the water drips from the ceiling of a cave, it releases a tiny amount of carbon dioxide into the cave air, and as it does, it can no longer hold all its dissolved calcium in solution. So, the calcium precipitates out, crystallizes very slowly into a tiny deposit of calcite. Drop by drop, year by year, century by century, a stalactite grows from the ceiling. Stalactites grow at about 1 centimeter per century. Some stalactites in ancient caves are meters long. They have been growing since before the pyramids were built, since before the first cities existed, since before people lived in the landscape above them. They are quiet monuments to geological patience. On the cave floor below, where dripping water hits and deposits its calcium, stalagmites grow upward. Sometimes, over thousands of years, a stalactite and a stalagmite grow toward each other and finally, silently, meet, forming a column of calcite that spans from floor to ceiling. That meeting has been coming for thousands of years. It happens without ceremony. Underground rivers eventually find their way out, emerging from cliff faces as springs or bubbling up from the ground in a valley floor. The water that emerges from a limestone spring is rich in dissolved calcium, clear and cold, and it tastes slightly mineral, slightly sweet. It carries its cargo of calcium to the nearest stream, and the stream to the river, and the river to the sea. Even the water you cannot see is part of the story. Even the river hidden in the dark beneath the fields, carving its invisible path through stone. It is flowing. It is carrying. It is contributing its small share to the salt of the sea, as it has for thousands of years, quietly, in the dark, without anyone watching. The ocean is not still, not even in its deepest, darkest places. There is a circulation system in the ocean so vast and so slow that it makes rivers seem hurried by comparison. Scientists call it thermohaline circulation. Thermo for heat, haline for salt. The ocean moves because of differences in temperature and salt concentration. Here is how it works, gently. In the far North Atlantic, near Iceland and Greenland, the ocean's surface is very cold. Cold water is denser than warm water. And this water is also salty because at higher latitudes, evaporation is less, but the salt remains. Dense, cold, salty water is heavy, and so it sinks. It sinks slowly, in great plumes, down through the water column, past 1,000 meters, past 2,000, past 3,000, until it reaches the ocean floor, and there it begins to move slowly, like a cold river along the bottom of the sea, flowing southward along the ocean floor, carrying its cold and its salt through the dark. This cold, deep current flows south through the Atlantic, around Africa, into the Indian Ocean and the Pacific. It takes roughly 1,000 years to make the journey. 1,000 years for a parcel of water to travel from the North Atlantic to the Pacific Ocean floor. Your ancestors who lived 1,000 years ago were breathing when the water that now flows along the ocean floor near Japan first sank from the surface near Greenland. Eventually, the deep water warms slightly, becomes less dense, and rises back toward the surface. It rises in the Pacific and the Indian Ocean, carrying nutrients from the deep, minerals and organic matter that have been accumulating on the sea floor, up into the sunlit zone where phytoplankton can use them. These upwelling zones are among the most productive in the world, teeming with life fed by the minerals that rose from the depths. The warm surface water flows back westward, warms further in the tropics, and eventually makes its way back to the North Atlantic as the Gulf Stream, that great river of warm water that flows northward along the east coast of North America and then across to Europe, bringing warmth to Ireland and Norway and Iceland, keeping those places much warmer than they would otherwise be at their latitudes. Salt is essential to this whole circulation. Without the salinity difference between surface and deep water, without the density that salt provides, the deep water would not sink, the current would not flow, the nutrients would stay on the bottom. The warmth would not be distributed. The whole system depends ultimately on the minerals that rivers have been carrying to the sea for billions of years. The ocean is a system. Everything in it is connected. The salt is not just sitting there. It is working, driving currents, distributing heat, sustaining life. It is one of the most important forces in the climate of the whole planet. And it all began with rain on rock and a raindrop finding its way downhill. There is something so peaceful about knowing the world's systems are all connected, all moving, all working together. If this story is helping you rest, a gentle like would mean the world to us. And the playlist is full of more nights like this one. Not all ancient seas are still filled with water. Some of them dried up over millions of years as continents shifted and climates changed, leaving behind only the salt they once contained. Vast, flat, blinding white deposits of mineral that once carpeted the floors of warm, shallow seas. The Salar de Uyuni in Bolivia is the largest salt flat on Earth. Nearly 11,000 square kilometers of white salt crust, flat as a table, sitting at nearly 4,000 meters above sea level in the Andes. It was once the floor of a great prehistoric lake that dried up thousands of years ago, leaving its salt behind. After rain, when a thin sheet of water covers the surface, the Salar de Uyuni becomes the world's largest mirror. The sky reflects in it perfectly. Clouds, sun, blue sky, everything doubled, the line between earth and sky erased. You stand on the salt, and you seem to be standing in the middle of the sky, surrounded above and below by the same endless blue. The Bonneville Salt Flats in Utah are another ancient lake bed. The remains of Lake Bonneville, which we mentioned earlier. The surface is so flat and so firm that it has been used for land speed records for over a century. Vehicles race across the white salt at extraordinary speeds, and the flatness stretches to the horizon in every direction, uninterrupted. In these salt flats, you can sometimes find the remnants of the ancient sea in very tangible ways. Ripple marks in the rock beneath the salt, the same gentle ripples that wind makes in shallow water, preserved in stone for millions of years. Tiny fossil shells of creatures that lived in that ancient sea, compressed into the sediment layers. Sometimes evaporate deposits, layers of salt and other minerals left behind by evaporating ancient seas, are found kilometers underground. The salt domes of the Gulf of Mexico and the North Sea were formed by ancient seas that evaporated 300 million years ago, their salt compressed and deformed by geological pressure until it moved slowly upward through overlying rock like a slow liquid, forming underground pillars of pure mineral. These underground salt domes are sometimes used as storage caverns, spaces carved out of the pure salt, stable and dry and chemically inert. used to store things that need to be kept in perfectly dry conditions. The salt that was once the floor of a tropical sea 300 million years ago now quietly holds reserves of oil or natural gas or compressed air in the dark. The salt endures. In the flat, blinding white of a Bolivian salt flat under the noon sun, or in the dark of an underground cavern a kilometer below the Gulf of Mexico, it is the same mineral, the same ancient chemistry, the same gift of rivers and time, waiting patiently as it has always waited, as it will always wait. There is a particular quality of light that belongs to water, not just the way water reflects light, though that is beautiful enough, but the way light moves through water, changes because of water, behaves differently when it touches water's surface. When sunlight hits the ocean, some of it is reflected from the surface. That dancing, shimmering pattern of light that moves with the waves. Some of it passes through the surface and enters the water, and in the water it begins to change, Water absorbs red wavelengths of light first. They disappear within the first few meters, then orange, then yellow. By the time you are 30 or 40 meters below the surface, only blue and violet light remains. The deep ocean is blue not because of anything special. It is blue because all other colors have been absorbed, and blue is all that is left. Divers who have been deep underwater describe the quality of the light as extraordinary, dim and blue and shadowless, coming from everywhere and nowhere at once, giving everything a gentle, diffuse luminosity. Fish down there look blue. Hands look blue. Everything is washed in the same soft, cool light. At night, the ocean has its own light. Bioluminescence, the ability to produce light chemically, evolved independently in many marine creatures. Certain plankton called dinoflagellates flash blue-green when disturbed. On the right night, on the right coast, a swimmer moving through warm water will leave a trail of cold blue fire behind them. Every movement, every wave of an arm lighting up with brief, ethereal light. The salt in the water plays a role in bioluminescence. The chemistry that produces light in these organisms depends on the mineral environment of the ocean to function properly. The salt water is not just a stage for this light. It is part of the mechanism. Sailors have seen bioluminescent seas for as long as humans have sailed. They called it sea fire, or the burning of the water. Sometimes whole bays glow at night, their shores ringed with cold blue light. Sometimes a ship moving through a bioluminescent plume will leave a glowing wake that stretches for hundreds of meters behind it, visible from miles away. Imagine lying on a warm beach on a dark night. The stars are out. The ocean is gently luminescent, just barely, just a faint blue glow where the waves break on the shore. The sound of the waves is slow and even. The salt smell is strong. The air is warm. Every now and then, a wave breaks and releases a brief cold light that fades before the next wave comes. There is nowhere in the world quite like that. And you can go there right now in your imagination and rest. Rain has been falling on this planet for over 4 billion years. The first rains fell on a young Earth that was nothing like the one you know. A planet still hot from its formation, with no continents yet, no life, just a vast shallow ocean under a sky thick with water vapor and carbon dioxide. Those first rains were warm. The ocean they fell into was warm. And they fell not as a gentle shower, but as sustained, heavy rain that lasted millions of years, as the earth slowly cooled and the water vapor in the atmosphere condensed and fell, condensed and fell, until the oceans were full and the sky above them was clear enough that rain became seasonal and variable rather than constant. The chemistry of that first rain interacting with the first rocks, the first rivers carrying the first minerals to the first sea, set in motion a cycle that has been running ever since, without interruption. Every rain that has fallen since is part of the same cycle. Every river that has ever flowed has contributed to the same sea. Every grain of salt in the ocean today has been there in some form for a very long time. Rain knows how to find the sea. It doesn't always take the direct route. It might spend 1,000 years as groundwater moving slowly through limestone aquifers. It might spend 100,000 years locked in a glacier. It might spend several years in a large lake, circling. But eventually, always eventually, it finds the river, and the river finds the sea. The word for this patient persistence of water is drainage. A drainage basin, a watershed, is all the land that drains into a particular river system. The Amazon watershed covers 40% of South America. The Mississippi watershed covers about 40% of the continental United States. Every drop of rain that falls within that watershed will, if it doesn't evaporate first, eventually find its way into that river. You are almost certainly living within a watershed right now, somewhere near you, maybe just a few kilometers, maybe farther. Water is gathering and flowing toward a river. That river is flowing somewhere, and somewhere, eventually, it reaches the sea. Rain doesn't know where it will go when it falls. It just flows downhill, follows gravity, takes the path of least resistance, gathers with other water, becomes part of something larger. There is a gentleness in that, a surrender to the shape of the land, an acceptance of the direction the ground slopes. You don't always have to know where you're going. Sometimes you just have to follow the slope of things, gather with others, and trust that eventually you will reach somewhere wide and open and still. We're so glad you're here tonight. If there's a topic you'd love to hear on the Sleepy Science Channel, trees, stars, caves, clouds, leave it in the comments. We read everyone. And don't forget to check the playlist for more peaceful nights. The night is very quiet now. Somewhere, rain is falling on a hillside. It is a soft rain, the kind that doesn't make much noise, just a gentle, continuous whisper against the leaves. The rain soaks into the soil. It finds the rock beneath. It begins, patiently, to dissolve the first few atoms of mineral from the stone. Somewhere, a small stream is moving through a dark forest. The trees are still. The water catches a little light from the moon and throws it back in small, shifting pieces. A frog sits on a stone at the water's edge, motionless, listening to the sound of its own world. Somewhere, A great river is moving through a sleeping valley. The current is slow and deep. The banks are quiet. Nothing moves but the water and the occasional leaf spinning in a gentle eddy near the shore. Somewhere, an estuary is shifting with the tide. The water moves in and out, the way breathing moves in and out. Salt marsh grasses stand in the dark. A single heron stands in the shallows, head tucked under its wing, asleep. And everywhere, always, the ocean, wide and dark and deeply, steadily breathing. Its surface moves in long swells that have traveled thousands of miles. The salt is there, dissolved and invisible, 3.5 parts in every 100, the same concentration it has held for hundreds of millions of years. The water cycle is turning as it always turns. Rain falls clean. Rivers carry their invisible cargo. The ocean keeps what the rivers bring. Water evaporates and rises and becomes clouds and falls again as rain. The minerals stay in the sea. The water goes around again. Nothing is wasted. Everything is kept or returned. You are part of this cycle too. The water in your body has been through the ocean. It has been in the clouds. It has fallen as rain on mountain ranges that no longer exist, flowed through rivers that dried up long ago, rested in lakes that have become deserts. The water in you is ancient. It has been everywhere. And the minerals in you, the sodium in your blood, the calcium in your bones, the potassium and magnesium that keep your heart and muscles working softly and steadily through this night. These were once in stone. They were released by rain. They were carried by rivers. They were kept for a long time by the sea, before the sea found a way to put them into living things, and living things eventually found a way to put them into you. You are made of river-carried stone. You are made of old seawater. You are made of rain and time and patience. And right now, you are resting. Your breathing is slow. The room around you is warm and still. Whatever weight the day put on you is beginning to dissolve, the way salt dissolves in water, slowly, gently, without effort, until it is simply gone. Let your eyes close if they haven't already. Let your hands lie open. Let your jaw unclench just a little. Let your shoulders settle down. There is nowhere to go. There is nothing to figure out. The ocean is out there in the dark, steady and salt and old, and it has been keeping its balance for longer than you can imagine. You are safe. You are warm. You are held by everything that has ever been patient, by stone and rain and river and sea. Rest now. Good night.